Okay, so chapter 11. This is sequences. When will the notes from yesterday? It will be the notes from yesterday. It will be posted during the weekend. I will create a video. So sequences. Okay. So section, we are going to start 11.1. So let's first see what is a sequence is. Okay. So sequence. So sequence, you will have terms like this: A sub 1, A sub 2, A sub 3, A sub 4, like that, discontinuous. So you will get a list of numbers. So you see, this is a list of numbers. And also notice that this is in ordered pairs. Okay, so it is in order, because A1 and then A2, A3, it is in order. So sequence is a list of numbers and it is in orders. So let's see how to write a sequence. So the notation, we write in curly brackets. So it is A1, A2. This is one way of writing a sequence. And also another way is you can just write one term. So if you consider just one term, this is AN, just one term of the sequence, A sub n. And then from n equals to 1, we can go to infinity. This is one way of writing. Another way is you can just write in the curly bracket A sub n. Okay. Okay. Another important part that you have to see whenever you see a sequence, when this name occurred. So you will notice this is always positive integers, right? Because here you see 1, 2, 3, 4, always positive integers. Okay, so sequence, we write it always in a positive integers. So every positive integers integer n, there is a corresponding number A sub n, and so a sequence can be defined as a, so this as a, I will write the other word, but whenever, can you read this note? Every positive integer n, there is a corresponding number A sub n. Whenever you read this, what do you think? Like, have you ever come across a definition like this? What is next to an? Next to an, sees this. So it's just so. So a sequence can be defined. Okay, can you read this and let me know, have you come across a definition like this? For each number, there is a corresponding number. For each integer, there is a corresponding number. When you read this, what comes to your mind? This is a definition of what? Anyone? So for each integer, there is a corresponding number. Yes, very good, Emma. It's a function. So you see, what is a function? What is a function? Function we define as f. For each x, for each x input, we get an output as x plus 1. Okay, whenever you when x is equal to 1, then your f at 1 is equal to 2. Whenever you give a number, so function is like a machine. Whenever you give a number to the machine, output there will be a number. So think sequence is also like that. So sequence is, it is also like a function. Okay, so this, so for function, so every positive integer n, there is a corresponding number a. So this is also a function. As a function, then the domain is, so domain is all the x values, right? In a function, domain means all the x values or all the inputs. Here, what is the input? It's all the positive set of positive integers. So this means if the positive integer n is equal to 2, the corresponding number is a sub 2. Okay, so if the n is equal to 3, the corresponding number is a sub 3. Like that. So it is like a function. Okay. So here we write a sub n instead f at n. Like here, instead f at n, we write a sub n. But it's a similar idea for the value of the function at n. Okay. So always, whenever you see a sequence, that means it's a set of functions. So let's see an example. A sub n is equal to 3n plus 4. So this is a function. And in the sequence, this is called the n term of the sequence. Okay. Okay, so can you all find, list the first 4 numbers of the sequence. Numbers are, we call terms of the sequence. That is, you have to find first, when n is equal to 1, the first term is a sub 1. When n is equal to 2, a sub 2. When n is equal to 3, a sub 3. Can you tell me what are the 4 terms of the sequence? 7, 10, 13, Kyla. Yes, I see. Correct. So the first term, when n is equal to 1, so you just substitute n is equal to 1 here. So 3 multiplied by 1 plus 4, you will get 7. Okay. So 3 multiplied by 2, you will get 10. 3 multiplied by 3 plus 4, you get 13. 3 multiplied by 4 plus 4, you get 17. Sorry, it's 16, right? 16. Okay, so these are the 4 terms of the first 4 terms of the sequence. If I write as a sequence, so your sequence will be curly brackets. For the first term is 7, second term is 10, 13, 16. This will go on. Okay, so this is called the first term. This is called the second term. Like that. This is third term, fourth term. It goes on. Okay. Now, if you see, so now let's see if n goes to infinity, what happens? So consider now if n, that is all the positive integers, positive number integers, if the positive integers goes to infinity, if the values of sequence increases, increases without bound. I will explain more mathematical term of bound later in this chapter. Increases without bound. That means if the a sub n goes to infinity without any bound, means it just goes to infinity without any number. So we call this as diverges. Okay. And then if, so this is, so we can write this as a limit term. So limit, if n goes to infinity, your n term, that is a sub n, goes to a number. If this is a number, then we say sequence is converges. So if it is goes to a number, sequence is converges. Is converges. But if, right in the above, I explain if n goes to infinity, your n terms goes to infinity or negative infinity, then we say this sequence doesn't exist. So we write that as DNE. This means do not exist. So sequences doesn't exist. Doesn't exist. And we call that sequence as diverges. Diverges. Because it doesn't converge to a particular number. Okay. Okay, so let's do some examples. First example, a sub n 1 over 3 to the power n. You have to check whether this sequence is converges or diverges. First, first write the 4 terms of the sequence. Can you all find what are the 4 terms of the sequence? First four terms. One over three, yes, William. Good. So it's 1/3. Yes, Mallory. So just find when n is equal to 1, that is 1/3. When n is equal to 2, 1/9. When n is equal to 3, 1/27. 1/81. So this will goes on. Uh, so what can you say about this sequence? Is it when as n goes to infinity, that is when n is increasing, what happens to your a sub n? Is it decreasing or increasing? Decreasing, right? So it is decreasing. So this is, so if I write it like this, decreases. So when n increases, your a sub n decreases. Okay. Okay. So if I write in arrows, n approaches to infinity, a sub n goes to, then if n goes to infinity, what happens to a sub n? When it is n is getting larger and larger, a sub n is approaches to 0. Yes. So it approaches to 0. So that means we can write this as a limit term. So lim n goes to n approaches to infinity, then a sub n is equal to 0. Okay, so if I write the term a sub n is this, so this approaches to 0. So then we can say your sequence is diverges or converges. It is convergent, right? So your sequence is converges. Your sequence converges. Okay, so let's see another one. Another example. A sub n 8n over 3n minus 1. Can you check whether this is converges or diverges? The sequence is converges or diverges? Can you check? Diverges, convergent. I get both two answers. Let's see for others then. So you can use your limit knowledge here. In what you learned in Cal 1. Limit techniques. Converges, Kyla. Matthew, converges. Yeah, I see most of you have got converges. So let's see how Okay. Okay, so let's see how to do this. So whenever you have something like this, the technique that you can use is Mallory diverges. Okay, so let's see. So the technique that you can do is, you already know that we learn when n goes to infinity, 1 over n is 0, right? Okay, so we can use this technique to solve this problem. How are we going to do that? We are going to divide all the terms, that is this, this, and this, divide by the highest degree, by the highest degree of n term, by the n term. The degree should be the highest. So what is the degree of n here? The highest is just 1, right? So we are going to divide everything by n. So if we divide everything by n, then what happens? This get cancelled, this get cancelled. So you will end up of getting 8 over 3 minus 5 over n. Okay. So this is your a sub n. Then we can find the limit, because we need to check whether diverges or converges. To check that, we have to take n approaches to infinity. So limit n approaches to infinity, 8, 3 minus 5 over n. So we can use limit of 8 is, limit of a constant is again constant. Limit of a constant, it's a constant 3, minus limit n approaches to infinity, 5 over n. So if we take 5 in front of the limit, then we will have again this kind, right? So here, if n goes to infinity, 3 minus 0, so that is 8 over 3. Okay, so then since the when n approaches to infinity, since we get a number, then we can say the sequence is converges. Sequence converges. Okay, so the only new part here is sequence, the word. The other parts, it's just Cal1. You have to use your limit knowledge and now to show that you get when n goes to when n approaches to infinity, you have to show that n term is a number to show it converges. Okay, so let's do another example. And also, so this is one way of showing converges. That means you can find the limit n goes to infinity, whether it is L or infinity. If it is L, sequence converges. If it is infinity, sequence diverges. So this is one way of showing converges or diverges. Another way is you can draw the graph. Okay, so if we draw this graph, if we draw this graph, I will draw to you. So you will get, this is horizontal asymptote as 8 over 3. This is x is equal to 5 over 3. This is a vertical asymptote. So your graph will look like this. Okay, so now imagine, visualize. So if we say sequence is convergence, if a sequence is converges, because we showed that this sequence is converges, then you will find, you will get a horizontal asymptote. What is this horizontal asymptote? How do you get horizontal asymptote? We get horizontal asymptote whenever, remember, whenever x, from college algebra, we get a horizontal asymptote whenever x approaches to infinity. Your function will approach us to a number, okay, any number. So let's say just a, this is just a number. So this is horizontal asymptote. To get the horizontal asymptote, I will just recall, to get the horizontal asymptote. How do you get the horizontal asymptote? Here, so m to the power m, so 1 minus 1, and a polynomial. You have to write a polynomial, and let's say ym, a minus 1, ym minus 1, and y to the power n, n minus 1, y to the power n minus 1. So if degrees are, this is like a note from college algebra. So if degrees are equal, that is m is equal to n of y variable, then your horizontal asymptote is leading coefficients, a sub m divided by a sub n. So I'm just recalling only one case. If you can't remember how to find the horizontal asymptote, check the notes, or Google it. So what happens if the degree m is greater than n? What is the horizontal asymptote? If the degree m is less than n, what is the horizontal asymptote? You can check. Okay, that's homework. You don't have to submit, but just read like how to find the horizontal asymptote, because we can show if without finding the limit or anything, because sometimes some questions will be easy if you draw the graph, and if you identify a horizontal asymptote, so that means the sequence is converges. Okay, so that's the second way. So I wrote it here. I will write again. If there is a horizontal asymptote, this means the sequence converges. Just Okay, so if I write this, so this is like a function, this is a function. If I draw this in terms of sequence, it will look like this. Because sequence is always points, right? Always numbers. So you get discrete, you get points, discrete. We have discrete points here. Because it's a sequence. Okay. By the same idea, what did we do here? We draw a graph. By the same idea, can you all tell me a sub n sine n? Can you tell me whether this converges or diverges? You can draw the graph or you can take a limit. What happens? Is it converges or diverges? What is the graph of a sine curve? Just draw the graph and let's check. Kyla said diverge. Yes, diverges. Who likes to answer why it is diverges? Yes, Colby? Why it is diverges? Who likes to answer? There's only a word because there is. Yes, very good. Because there is no horizontal asymptote. That's the idea. Okay, because we talk only about the horizontal asymptote. We can say the sequence diverges or converges by looking at the horizontal asymptote. But here, when you draw the sine curve, your sine curve will look like this. This is a periodic function. This is sine x. So here you will see this is 1. Here, this is -1. There is no, when n approaches to n, there is no horizontal asymptote. Because it can be sine x can be 1 or -1. So that means it doesn't exist. So limit when n goes to infinity a sub n, we say it is do not exist. Because it always oscillates between 1 and -1. So, and there is no horizontal asymptote. This is do not exist, or we can say it is diverges. Okay. Okay. What about this? Now let's do another example. Mm, what about this? A sub n sine n over n. So now we are going to check whether this sequence is diverges or converges. Okay. So we learned from the previous example. Let's do this because I want to introduce a new concept. So here we saw the sign is always, it oscillates between 1 and -1. Okay. So sign varies from -1 to 1. Okay. So if we just say, so let's trigger when because this means, let's say some terms, how to get the terms when this is divide by n, that is when -1 divides by n or 1 divide by n. When n goes to infinity, what happened to these two? How do we get this -1 and 1? Because sign, it is varies from -1 to 1. That's how I get it. So, but here in this n term is sign divide by n. So, -1 divide by n and 1 divide by n. What happens if n goes to infinity? This term will become what? Both approaches to 0, right? When n goes to infinity, both approaches to infinity. -1 over n approaches to, 0. 1 over n the approaches to 0. So that means, so we get a number, that means it's converges, right? Okay. So this is like scratch work. So let's see how to prove this. So I'm going to introduce a new theorem. This I guess you have learned in TAL 1, but let's recall. This is called, so how to show this work? How to show the sequence is convergent, converges. So we use squeeze theorem. What is squeeze theorem say? So this is the note. What is squeeze theorem say? So the basic idea is if three functions are given, this is your basic function. If we show that limit n x goes to infinity of gx is a number like L, and also limit x goes to infinity, your hx is a number, just a second. Okay, so if we show if x goes to infinity, your g function is you get a number, and when limit goes to infinity, you get a number. That means if g and h has limits, and it should be same limit, then we say the limit of middle function has a limit, has the same limit, as the same limit. So this is squeeze theorem. What is the idea? So this is the basic function you have, and if you see, there are two functions. So the basic function is greater than g and less than this h function. But if you show the limit of the g function and the limit of the h function, you get the same value L. Then we can say the limit of the middle function, that is f function, has the same limit. Okay, that's squeeze theorem. So you can apply this squeeze theorem in problems. Okay, so we can use squeeze theorem in this question too. So let's see how to use this squeeze theorem. So if I write the same limit means x goes to infinity, your f function will also get L. Okay, now let's apply this squeeze theorem to the problem. So here we have sine n. So your question is a sub n sine n divide by n. Okay, by the graph, you know sine n is between 1 and negative 1. This is by the sine curve. Sine curve. Basic graph of the sine function. Then in the n term, a sub n, it is divided by n. Okay, this is divided by n. So we can make that function by dividing all the terms by n. Okay. Okay, now we check the limit of this function. So that is limit n approaches to infinity. You all found that this goes to 0. It approaches to 0. And also limit when n approaches to infinity, 1 over n is 0. Then we can say by squeeze theorem, because these two functions have the same limit, then we can say limit when n goes to infinity, sine over n is also 0. Okay, so this is convergence. Sequence is convergence. Therefore, the sequence is convergence. Okay. So this is just one method, like by you can check whether you can use squeeze theorem. So let's do another example. This is example. Your a sub n is equal to natural log n to the power 4 over 5n. So we need to check the limit of the n term. Can you try this? Can you try a method you have learned in Cal 1 and solve this? Let's see whether anyone can remember how to solve this. So here also we are using just a theorem, a rule, I guess. It's a rule, not a theorem, it's a rule. Let's see whether anyone can remember. Yes, very good, Melody. We are going to use L'Hopital's rule. Okay, so very good. So let's first see how to use the L'Hopital's rule. So here, identify this is a power. There's a power inside in a log function. So we can take the power out first. That's the first thing you can do. So here, if you take the power out, we have ln n over 5n. Okay. Okay. Now we can use, so we have to find when n approaches to infinity, what is the value of this? Now we can use L'Hopital's rule. Now use rule. Okay. So what is L'Hopital's rule? That means you can differentiate the numerator and the denominator. Okay. So this is same as if we differentiate with respect to n, the numerator, and we can also differentiate the denominator. That is L'Hopital's rule. So this limit is equal to this one by L'Hopital's rule. And then if you differentiate, what do you get? So here it's, I'm sorry, this should be n, right? This is n. So if you differentiate, what do you get? As in the numerator, what do you get when you differentiate? 4x, there is no x. 4n, yes, let's see. 4n, 4n, no, 4 over n, right? Because uh, the differentiation of the log function is 1 over n. So it is 4 over n. So that's the numerator. Good. Then I see many correct answers. Then the differentiation of the denominator is just 5 because differentiation of n is just 1. Okay, so then we can take the constant now, that is 4 over 5, limit n approaches to infinity, we have 1 over n. So what is the answer here now? Zero. Okay, so is it converges or diverges? So we found limit n approaches to infinity, and to the 4, 5n is equal to 0. So yes, good. So this sequence is converges. Converges. Okay. So this, yeah. So to show the sequence is converges, what do we use? We use the limit definition. That means if you take the limit when n goes to infinity, if you get a number, we said the sequence is converges. Or else we can use the graph and show if we find a horizontal asymptote, that means the sequence is converges. And also in this example, we used the L'Hopital's rule to show that limit exists. So this is one way. So same thing, you can, is there a possibility to scroll up? Yes, sure. Micah, is that enough or you want more to scroll up? Okay. Okay, so let's do another example. Can you all find, because we use the L'Hopital's rule here, can you all find what is, whether this sequence is converges or diverges? Converges. QML converges. Okay, let's see how to do this. Converges. I see some answers. So let's see how to do this one. So we have to find when limit n goes to infinity, what happened to this? 1 over n. So we can think this as, so n is same as, n we can write again, you can visualize 1 divide by 1 over n. This is, so n is equal to 1 over 1 over n, right? It's the same thing. I represent n in this way. So if we represent in this way, we can write, instead of this n, we can write sine 1 over n, 1 over n. Okay, because it's the same thing. I represent n in terms of this term. Okay, now we can use L'Hopital's rule. By using L'Hopital's rule, so that means this is equal to, we take the first derivative of the numerator and denominator. So the derivative of the numerator becomes cosine 1 over n. And then by chain rule, we have to multiply by the differentiation of the inside term. So the differentiation of, so when you differentiate 1 over n, you will get, this is minus n to the power negative 2. Okay, because 1 over n is same as n to the power negative n, right? So if you differentiate, you will get this. So we can multiply by the differentiation, that is negative n to the power negative 2. And when you take the differentiation of the denominator, it's the same thing, negative n to the power -2. So this get cancelled. So you will have limit n goes to infinity, cosine 1 over n. So when n goes to infinity, this whole thing inside the parenthesis, this becomes 0. So what is cosine 0? It's just 1. Okay, so this sequence does limit n goes to infinity, n multiplied by sine of 1 over n, this is equal to 1. Therefore, the sequence converges. Converges. Okay. I mean, this is just one way. You can use any methods that you learn in Cal 1 to solve the limits. So this is just, I showed how to use the L'Hopital's rule. I like to use L'Hopital's rule. Sometimes it's very easy, like without using the other techniques. Okay, so what about this one? Let's see another example. Now your n term will look like this, n plus 1. Oops. Okay, so whether is it converges or diverges? Can you all try this? So let's, what do you think, whether it is diverges or converges? How do we solve this? So to understand this, let's recall, just use some numbers. So 8, so this means 8 multiplied by 7 multiplied by 6 multiplied by 5, and it goes to 1. Okay, so what about 7? This means 7, 6, 5, and goes to 1. So if 8 factor in divide by 7 factor in, then what do you get? So that means 8, 7, 6, 1, divide by 7, 6, 5, 1. So all these terms get cancelled, right? So you will only get 8. So we are going to use the same method here. Okay, we can use a sub n. We can write the numerator as n plus 1. And also another way, also we can write 8 factoring. This is equal to 8 multiply. I wrote it 7 multiplied by 6 multiplied by 1. This whole thing is 7 factoring, right? So we can write 8. This is equal to 8 multiplied by. So same method we are going to use here. So we can write this term as the first term multiplied by nth factoring divide by the nth factoring. So we can cancel. We will have n plus 1. Now take the limit. When n goes to infinity, what is the value of this? When n goes to infinity, what happens? N plus 1. Goes to infinity. So this is goes to infinity. Therefore, now this is not a number, so it is diverges. So the sequence is diverges. Diverges. Okay. 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 So now let's learn a new one after this. So now we are moving on to absolute value. So absolute value theorem for sequences. So the example we are going to do is, we are going to find whether this n term is converges or diverges. Okay, so we are going to use the absolute value theorem. What is absolute value theorem? So absolute value theorem is for sequences is, if n approaches to infinity, absolute value of the n term, I'm sorry, this should be infinity. If limit n goes to n approaches to infinity, then the absolute value of the n term is 0. If we show this, then we can say straight away, without showing like any calculations, we can say when n approaches to infinity, your n term a sub n goes to 0. This is absolute value theorem. Okay. So let's use this theorem to solve this sequence. So what you have to check, you have to take the absolute value of this n term. So can you all tell me what is the absolute value of enter. What is the absolute value of this term? Uh, I'm not asking the limit. I'm just asking just the absolute is just on if the what is Kyle asking? I'm just asking what is the absolute value of this term? This C is it just and if the sequence is only positive. So, Kyla, what do you mean by the sequence is positive? And with a positive domain. Another way. So let's, I see many correct answers, but we using every positive. Yeah, we use all positive integers, yes. So all positive integers. Uh, so this means absolute value means yes, you take all the positive values. Yes. So whenever you take the absolute value of any number, what you are saying is we are going to consider the positive value. So let's do then this example, then you will understand. So now this n term is you take the absolute value of this. So let's say n is just 1, then you will get negative 1 over n. Then the absolute value is 1 over n, because absolute value of a negative is always a positive, so 1 over n. When n is equal to 2, inside negative 1 over negative 1 to the power 2 divided by n, so it's just 1 over n again. So you always get, whenever n you get a positive integer, you always get negative 1 to the power n. When you take the absolute value of this is just 1. Okay, so you will end up of getting 1 over n. Okay, then we are going to use the absolute value theorem. What is absolute value theorem? We are taking n approaches to infinity of the absolute value of n. So what is this equal to? Okay, so to answer Kyla's question, so positive, so your sequence is positive, every positive. So this n is always a positive integer. Okay, but your value of a, that is a sub n, you can get a negative value or a positive value. Positive value, negative or positive value. Okay, but you're here, the what does it mean? This this whole thing, this n should be always positive. That means A1, A2, A3, like that. You cannot have A -1 or A -2. Okay, did I answer your question, Kyla? That's the idea. So we took the domain is always the input is positive values, but output we can get negative values or positive values. So what is the limit of this one? Kyra, did I answer your question? Yes. Okay. So then when you take the absolute value of the n term a sub n, this is n goes to infinity 1 over n. So what is the answer here? Zero. So it is 0. Okay. We are not done yet. We showed the absolute value of n a sub n is when n approaches to infinity 0. Then by absolute value theorem, then by absolute value theorem, then we can say limit when n goes to approaches to a sub n is equal to 0. Then we can say it's only because of this we can say then the sequence is converges. Okay. Okay, so what did we do? We didn't show this one. We showed this part. We showed the absolute value of the n term converges. Then by absolute value theorem, we can say the n term is converges. Okay, that's the absolute value theorem. So sequence is converges. Okay, any questions up to here? Next, I'm going to move on to a next new part. Okay, I see some questions. Okay, so let's move on to next part. Now we are going to learn about monotonic sequences. Okay, so let's see what is monotonic sequences. Monotonic sequences. So monotonic is sequences are sequences where it is always sequence is increasing or decreasing. So monetary sequences is a sequence always increasing. Don't forget it's or decreasing. So if the n term, whenever you take an n term, if the n term is increasing and, whenever you draw the graph, you will see if some questions are increasing and decreasing both in the graph, then that's not a monotonic sequence. Okay, so monotonic sequence is it's either increasing or it's always decreasing. Okay, so that's the monotonic sequence. So let's first see what is an increasing sequence. So because we have here increasing and decreasing. So what is increasing sequence? So increasing sequence is whenever you will see something like this, the first term is less than or equal to the second term of the sequence. I will write the sequence again. A1, A2. This is the sequence. This is the sequence. So if the first term, so we say this is as the first term of the sequence. If the first term is less than or equal to the second term, and the second term is greater than the first term and less than the third term, like that, always the terms are greater than the previous one, but less than the next term. Then we say, or you can say, or also you can say, or you can also show by looking at these first two terms. So A1 should be less than or equal to the second term. So if we divide both sides by A2, then the right hand side becomes 1. So because, because A2 is greater than A1, if you divide A1 by A2, A sub 2, it is less than 1. So if we show this or this, then we can say this is an increasing sequence. So then this whole thing is an increasing sequence. Okay, then what? Let's see what is a decreasing sequence. Decreasing sequence. So in the previous one, because it is an increasing sequence, we can say this is also monotonic increasing sequence, because it's only increasing, so it is a monotonic. Decreasing means the first term is greater than the second term, and second term is greater than or equal to third term, like that. Always the next term is less than the previous one, so it's always less. Also, if we consider these first two terms, this is one way. If we just consider the first term and the second term, first term is greater than the second term. If we divide both sides by A sub 2, then also we can say if the first term divided by the second term is greater than or equal to 1. If we show this also, we can say that the sequence is increasing. Okay, so I mean decreasing. The sequence is decreasing. Okay, so if we show this also, we can say this is monotonic decreasing sequence. Okay, so if we visualize this, how to visualize this increasing sequence and decreasing sequence? So let's visualize this increasing sequence or monotonic increasing sequence. If I draw the graph, so always you will get discrete points. So you see, it is when n goes to, like, it is always increasing. So always increasing. Always goes up. Goes up. So it is monotonic increasing. But about if it is a decreasing sequence, let's visualize this. So if we visualize this, the decreasing sequence is it's always decrease. Whenever the n goes to infinity, you get lower values. So this is always decreasing. Goes down. Stop. Okay. Okay, what about this? Can you tell me whether it is monotonic or not? No, right? It's not monotonic because it's increasing and decreasing. So it's not monotonic. Increasing and decreasing. So it's not monotonic. Okay. So now let's see whenever like a n term is given, how to check whether it is monotonic or not. So let's do an example. N is a sub n is equal to 3n divided by n plus 2. Is this a monotonic sequence? Or if it is monotonic, is it increasing or decreasing? So can you first find what are the four first terms of the sequence? What is a sub 1, a sub 2, a sub 4? One, 3/2. Okay. Okay. So we will get, so when n is equal to 1, you will get 3/3. So that's just 1. When n is equal to 2, you will get 6/4 and 9/5 and just 2. Okay. Can you find these two in decimal places? So if we find in decimal places, because we need to check whether it's increasing or decreasing. So 6/4, if you write as a decimal place, you will get this is as 1.5. This is 1.8 and this is 2. Okay. By looking at these four terms, what can you say? Is the sequence is increasing or decreasing? Increasing, right? It's increasing because if you write 1.5, 1.8, 2, this is the increasing sequence. And we can say it's a monotonic sequence. Monotonic sequence. Because it's always increasing. Okay. So, but how do we prove this? So we can say it is a monotonic sequence if we see four terms and we can straight away it's monotonic. How to prove this? Because we have to know about the proof also. How to know the proof? So, like I said, when increasing, we showed that if the first term is less than or equal to a2, We need to show something like this. Okay, we need to show this. Show this. But if we write in a generalized form, so what we have to show is, we have to show the n term is less than or equal to the a sub n plus 1, the next term. Okay, this is what we have to show. We must show this is true. We must show that this is true. True. So let's see how to show that this is true. So you just substitute what is a sub n. So a sub n is 3n over n plus 2. Okay. And the right hand side, now instead of n, we substitute, we replace all the n's by n plus 1, like the functions we did. Remember, if you have f at x, if you have x plus 1 in the function, what you did, you replace x in terms of x plus 1, because sequences are each term is a function. So replace n with n plus 1. N plus 1 plus 2. So this means this is 3n, n plus 2. Just distribute this. So 3 multiplied by n plus 3. You will get n plus 3 in the denominator. Okay. Okay. Then what we have to do, so you see both sides, both left hand side and right hand side, both are in fractions. We can get rid of these fractions. So we can get rid of this part by multiplying by n plus 3, both side by n plus 3. Okay, so then we can get rid of this one. So in the left hand side, you will have 3n multiplied by n plus 3 over n plus 2 less than 3n plus 3. Then we can get rid of this one by multiplying both sides by n plus 2 plus 2. So this get cancelled. So now you will have 3n n plus 3, 3n plus 3, n plus 2. So distribute the left hand side, you will get 3n squared plus 9n. The right hand side, if you use the FOIL, let's use the FOIL. So 3n squared plus 9n plus 6. Okay. So you see this term, both are common in left hand side and right hand side. So you can just cancel. You can just cancel. And here in the left hand side, you have 0, and the right hand side, you have 6. Now what you have to ask yourself is whether this statement is a true statement. Is it a true statement? Is it a true statement? Is 0 less than or equal? I mean, it's true, right? It's greater, 6 is greater than 0. So it's a true statement. So since it is a true statement, we can say the first inequality. So first inequality was we found an is less than or equal to a sub. So this equality is true. So we can say, because we show this is increased, so therefore the sequence is increasing. Increasing. Okay. So we can say this is increasing. So this is monotonic, tonic, increase in sequence. Sequence. Okay. So same thing. Can you all check this example? So same way, take some time to find whether these are the same steps. Can you all check whether this one is monotonic? If it is monotonic, I mean, is it monotonic increasing or monotonic decreasing? So this will be the last question for the day. So the first step is just take, because in the questions normally they will ask you first write the first 4 terms. What are the first 4 terms? What is A1? What is A2? What is A3? What is A4? Three over 4, okay. 9 over 16, okay. So 3 over 4, yes, right. 9 over 16, then 27 over 64, and 81 over 256. Can you all write this in terms of decimals? What are the decimals? So this you will get 0.75, Skylar 0.562, 0.4219, 0.3164. Okay, so what do you think this? Is it increasing or decreasing? It decreases, right? It's a decreasing sequence. Okay, so we have a rough idea. It is decreasing. Then, so it is decreasing. So like the previous one, if it is decreasing, what you have to show, oops, no, that's fine, Alex. So then what you have to show, we need to show that this, the generalized form, generalized AN is greater than the next term. A sub n is greater than or equal to A sub n plus 1. Okay. Okay, so here is we have A sub n, again we have 3 over 4 to the power n. Then what is A sub n plus 1? Instead of n, we replace n plus 1. So 3 over 4 to the power n plus 1. Okay. So we need to show that this statement is true. So 3 over 4 to the power n greater than or equal to 3 over n plus 1. So let's do this by, let's divide ln. Yeah, you can use ln also. Yes, but let's do like this. So remember I did something sorry. So let's divide because remember I said if A1 is A1 divided by A2 is greater than equal to 1, this is a decrease in sorry, this is a not this. So the other way around. So let's divide both sides by this term or the other way, anything you can do. 3 over 4 to the power n divide by the right hand side. Then the right hand side will become 1. Or you can divide both sides by 3 over 4 to the power n. It's up to you. Then you can write the denominator as 3 over 4 by power rules, because this n plus 1, we can use the power rule and write this is 3 to the power 4 to the power n and 3 over n, right? By power rule of exponents. Because if the same base is there, the power gets, we can add the powers. So you get this one. Now you will see this is same, right? So you get cancel. Okay, so now you have 1 divided by 3 over 4 greater than 1. So this is same as 4 over 3 greater than 1. Now you have to ask yourself whether it is a true statement. Is it a true statement? Is it a true statement? Yes, right? So it's a true statement, yes. So then we can say an is greater than a sub n plus 1, that is monotonic decreasing sequence. Okay.